They create a massive corpus of code across dozens of programming languages. The final mix. The team creates a final recipe for the training dataset. For example, 50% high-quality web text, 30% high-quality web text, 15% code, 5% academic papers, books, etc. This mixture is crucial for defining the model's final capabilities and biases. Phase 3: Infrastructure Setup. You can't train a 67B parameter model on a single computer. Procuring the compute. The boring detail. DeepSeek likely built or rented a supercomputer comprising thousands of high-end GPUs connected by ultra-high-speed interconnect. The cluster must be managed by a system like Kubernetes or Slurm. Building the training software stack. Frameworks. They use frameworks like PyTorch and Megatron DeepSpeed or Fairscale. These frameworks are not off the shelf. They are heavily customized to enable 3D parallelism. Data parallelism, splitting the data batch across multiple GPUs. Tensor parallelism, splitting the individual model layers across GPUs. Pipeline parallelism, splitting the model's layers across multiple GPUs. The boring detail. Engineers spend months optimizing this setup to achieve high MFU, a measure of how efficiently they are using the raw computing power of the GPUs. A 5% improvement in MFU can save weeks of training time and millions of dollars. Phase 4: Training. This is where the magic and the immense cost happens. Pre-training. The task. The model is tasked with the simple objective of predicting the next token in a sequence. By doing this over trillions of tokens, it learns grammar, facts, reasoning, and style. The boring detail. Hyperparameters. The team sets a learning rate, batch size, and optimizer. These are not guessed. They are found through small-scale experiment. The run, they start the job. It runs non-stop for weeks or months. The entire GPU cluster is at 100% utilization, drawing megawatts of power. Monitoring. Engineers monitor thousands of metrics: loss curves, gradient norms, GPU temperatures, network bandwidth. They have automated systems to checkpoint the model every few hours so they can resume from a checkpoint if the cluster crashes. Cost. At this scale, the pre-training run alone can cost $10 to $50 million in cloud compute or hardware costs. The chinchilla law. A critical decision is made about the model size and the amount of training data. The chinchilla paper showed that for a given compute budget, it's better to train a smaller model on more data. DeepSeek would have carefully chosen its 67B size based on this, training it on 2 trillion tokens. Phase 5: Post-training and alignment. The pre-trained model is a knowledgeable but uncooperative savant. It will complete prompts, but it won't follow instructions or be particularly safe. This is where it becomes an assistant. Supervised fine-tuning. The process. A team of human contractors creates a dataset of 10,000 to 100,000 high-quality prompt response pairs. For example, prompt: write a Python function to calculate the Fibonacci sequence. Response: def-fib, with an explanation. The boring detail. The model is fine-tuned on this dataset. This teaches it the desired chat or instruction-following format. This is a much shorter training run than pre-training. Reinforcement learning from human feedback or DPO. Step 1: Reward model training. The process. Human contractors are shown multiple model responses to the same prompt and rank them from best to worst. The boring detail. A separate model, called the reward model, is trained on these rankings to predict which response a human would prefer. This is a complex training process in itself. Step 2: Policy optimization. The process. The main model is further fine-tuned to generate responses that maximize the score given by the reward model, while also not straying too far from its original SFT state.